Now that we have laid out the concepts of mathematical proof and what we mean by axioms, theorems, proofs, etc., we can now talk about methods of proof. And I have a list of methods here, which is probably not exhaustive, so there are probably other methods of proofs, but these are the main ones that are used widely. And I'm going to talk about and give examples to some of them. And probabilistic proofs are a little bit involved, so I'm not going to really go into those. And we are going to talk about induction extensively. And computer-assisted proofs are quite new, actually. Well, naturally, because you need a powerful computer to do them. And they are also related to proof by exhaustion. And there is a very famous problem that was proven first using a computer, the four-color theorem in graph theory, which we will talk about in the very last week, I believe. And I'm going to touch upon that when the time comes. But essentially, that has a historical significance rather than practical significance, or maybe in addition to its practical significance, let's say, for being the very first problem or the very first theorem to be proven using computers. Okay, so now I'm going to go through these quite briefly, and I'm going to give very simple examples for some of them. And the first one I'm going to talk about is the direct proof. And here's an example. Let's prove the statement: if n is an even integer, then its square is also an even integer. Okay, we can use direct proof to show this. But before that, let's talk about, or let's think about what direct proof is. Now, here I have formulated this statement. You see, this says there exists a k, which is an integer, such that n is equal to 2k. So this means, you see, n is an even integer. Okay? And this, together with b, entails this. There exists a k integer such that n squared is equal to 2k. Now, these two k's are obviously different, but essentially what you are saying is if n is even, n squared is also even. What is this b here? B here is, well, I chose b here to represent the body of knowledge, let's say, in mathematics that we can use to show this. Okay, this includes axioms, this includes definitions, or maybe, if necessary, other theorems that you have proven before. Of course, one thing you have to be careful about is not to be cyclic. For instance, if you use a theorem to prove this statement, and then in the proof of that theorem, if this statement appears, that's a cyclic argument, which is not valid. Okay, you have to be careful about that. But in general, in mathematical proofs, we don't really lay out everything we know, because it's a huge list, of course, and we are not going to use everything. But the stuff we use also, we do not really put in this sort of form of an argument. Okay, so we sort of just lay out the path of the argumentation and leave it at that. If you would like to formalize it, it is possible, but for every proof, it would be tedious. And for even with this small example, it would be quite tedious, let alone a complicated theorem. So we generally do not do that. And here's the proof. It's quite simple, as you see. N squared is, well, by definition, is n times n, and since n is equal to 2k for some k, then this is equal to 4 times k squared. And here, of course, you see I'm referring to b as the definition of product, for instance, or taking the second power of a number, what it means, etc. So I'm not really explicitly stating everything I'm using. In a general sense, you have to do that, theoretically speaking, but we do not when everything is straightforward. So here I'm leaving it implicitly in this body of knowledge. Let's say, for instance, the set of integers is closed under multiplication, is one piece of knowledge we are using here. So if you multiply two integers, what you obtain is an integer. Okay, it's essential in this proof, but I'm not explicitly stating it. Okay, what I'm doing is I just write n squared is equal to 2k squared, which is equal to 4 times k squared, which I can write as 2 times k squared. And this here, since k is an integer, this is an integer, and 2 times an integer is an even number by definition of an even number, which means n squared is an even integer. Okay, so the proof is complete. Now this symbol you see here stands for QED, and it indicates the end of the proof. And what does QED mean? QED stands for this phrase in Latin, okay, and roughly translates that which was to be demonstrated, okay, and we usually say, and that completes the proof, or sometimes we say that was what we were trying to show, etc. Okay, and notation-wise, sometimes you see an empty square instead of a black one. So this is direct proof. Another one is proof by contraposition. If you remember what contraposition was, and you have an implication, P implies Q, and the contrapositive is not Q implies not P. If you remember, actually, these are equivalent. Okay, so proving one is equivalent to proving the other. So if the contrapositive of a statement is easier to prove, you prove that rather than the original statement. So here, let's look at an example. If n squared is an even integer, then n is an even integer. Now this is the let's say, a converse of the statement we have seen earlier. And instead of proving this given statement, I'm going to prove its contrapositive. And take the contrapositive, you switch the order of the implication, and then you negate both sides. If n is not an even integer, then n squared is not an even integer. This is the contrapositive of the original statement. Okay. Now, how to prove this? Since n is not even, if n is not an even integer, it is odd, obviously, which means it can be written as, for some k, 2k plus 1. Then take the square, because we have n squared here. Take the square of 2k plus 1. You have 4k squared plus 4k plus 1. So that is 2 times 2k squared plus 2k plus 1. This is some integer. So 2 times an integer plus 1 is an odd number. That means n squared is an odd number and not even. Okay? So at this point, we use direct proof to prove the contrapositive. That means the original statement, this one, has been proven too.